Hello everyone, and welcome to my channel. This is an educational channel. We look at theories of everything in depth and kind of show you how to use them, show you how they can benefit your life, help you with your paradigm shift and your transition into 5D consciousness, and your formation of a holistic worldview. Today is our 441st video that we have done on the reciprocal system of theory from Dewey B. Larson. In 1959, Larson proposed his two fundamental postulates about how the universe operated, and then took those postulates and through a process of deduction, an if this then that type of approach, he arrived at a theoretical universe and then wrote some books on kind of how his theoretical universe compared or coincided with the universe that was observed by the scientists. We are looking at one of his books here called Basic Properties of Matter that has to do with chemistry. And Larson was able to deduce a number of different equations for the from his postulates for the basic properties of matter, such as the melting point and the specific heat and the compressibility and the interatomic distance. And then he compared those numbers, those calculations, with the observed values that the scientists had compiled. And so we're going to look at some of the results of that from chapter 5 today, heat, just on basic thermal relations. And this is our second installment of that chapter that we started yesterday. Now, Larson's two fundamental postulates are mainly concentrated in his first postulate. The second postulate really just has to do with math and geometry, and there is really somewhat axiomatic, having to do with commutative mathematics and absolute magnitudes, and also Euclidean geometry. Now, some of Larson's followers have even rejected the second postulate in whole or in part, quibbling about the geometry of the universe. And it's not quibbling, but it is for us at this point, because we're trying to just get to the nuts and bolts, and that's more of a finer point that might come about later. Now, Larson's first postulate, however, is where the so-called meat and potatoes are, and that is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay. So the universe is not made out of matter, it's not made out of energy or anything else. It's made out of motion. And motion is the relationship between space and time. Motion, space, and time all come in 3 dimensions and in discrete units. There's many ramifications of that he worked out in his derivations. But basically, Larson is referring to a kind of motion that he calls scalar motion. The universe is composed of scalar motion, which is a motion that has a magnitude but has no specific direction. You can envision a scalar motion if you take a balloon and put dots on it with a magic marker. If you blow up the balloon, all the dots will be moving away from each other, but in no specific direction, and just outward. the outward motion of the balloon that Larson calls the progression. And if you turn around and suck in the balloon, all of the dots will be moving toward each other, but again, in no specific direction, or really in all directions. That's an inward scalar motion, or Larson would call it gravitation, analogous to a gravitational motion. And there is no direction of those motions. All the dots are moving away from all the other dots. All the dots are moving in every direction. Now, if you decide, though, to kind of stop that motion by assigning a reference point and saying, this point we will consider to be motionless, then you can start imputing directions to the other dots. And it will seem as if there is a force field there that all of the dots will be moving toward the one that you have deemed the reference point. If you're talking about an inward gravitational motion. If you're talking about an outward motion, then that it will appear as if all dots are being kind of ejected from that original dot and are moving away from it. But these directions are not part of the motion. They are part of the reference system. And so in Larson's system, he really does have three separate reference systems, or maybe more, but three relevant ones that we're going to look at here. He's got a spatial reference system, a temporal reference system, and then what he calls a natural reference system. The natural reference system is this balloon motion, this scalar reference system, and then once you kind of stop that motion and you assign a reference point, if the reference point is in space, then you have what he would call a spatial reference system. And this is comprised of 3 dimensions of space in a still frame, basically vector space, x, y, z coordinates, which I think I mistakenly called Euclidean, but it's really Cartesian coordinates. And so you have x, y, z coordinates in a still frame. And that's basically what we observe in the universe, in our environment of the universe. And to go along with that 3 dimensions of space, or coordinate space, we also have what he calls clock time. The time is progressing, flowing. It's always getting later and later and later, further apart. So that is a scalar motion in time, because the motion has no specific direction. And so what we have is we have a vectorial coordinate motion in space, but we have a scalar motion in time. Now, just keep that in mind. Now we're going to go to the space and time. Larson, unlike some of his predecessors who also proposed the idea of motion as the basis for their universe, Larson defined motion as the relationship between space and time. For Larson, motion is a fraction, with space or time as the numerator and time or space as the denominator. You can see that in the most basic kind of motion, speed. The bicycle's moving 15 miles per hour, 15 miles of space in 1 hour of time. Space over time is speed. And if you double the speed, then you would say the bicycle is now moving 30 miles per hour. Or equivalently, you can say the bicycle is now moving 15 miles per half hour. You can multiply the space or you can divide the time. That's a reciprocal relationship. So in the most basic kind of motion, speed, we do see that there is a reciprocal relationship between space and time. But Larson extrapolates that to all scientific phenomena are relationships between space and time. So they're basically fractions. Space or time is the numerator, time or space is the denominator. In Larson's system, energy is time over space. Matter is time to the third power over space to the third power. Pressure is time over space to the fourth power. Temperature, space over time. And momentum, space to the second power, or time to the second power over space to the second power. Force, time over space to the second power. And so on. So that serves as a great system for checking your measurements and stuff like that, checking equations of old and seeing if their units work out. It's much simpler than using the three variable unit system of the MKS. You can get rid of the mass. You can turn all your masses into TS, or T to the third power, or S to the third power. If you're going to accept the idea of a universe of motion, the first thing that you have to be able to accept is you have to be able to accept motion preceding anything moving. So motion comes first before anything moving. You have to be able to conceive of this empty universe that has motion already. And that's what Larson calls the progression of the natural reference system. And that is an omnipresent, eternal motion. It's always there, ever present. And you can get the magnitude of that motion. The magnitude of the motion is 1. And that comes from the discrete unit postulate. Space, time, and motion are all quantized. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. And same with motion. So a unit of space turns out to be about 1/500,000th of an inch. A unit of time turns out to be about 1/6.5 quadrillionth of a second. And the unit of time, the unit of speed is 1 unit of space per 1 unit of time. Remembering that space over time equals speed. So 1 over 1, and that works out to be what Larson calls unit speed, or the speed of light. So this is the background speed of the universe. He calls it the 0 point, or the null point, the neutral point, or the progression of the natural reference system. Motion outward at the speed of light in all directions. And this is, and you have 3 dimensions of this, 3 dimensions of motion. So that's really what he would call the natural reference system. Okay, so we've got the spatial reference system, and then we've got this natural reference system, the empty universe, really the source of everything to come in this universe. And then you can recognize this as being really the midpoint, or the neutral point. And so that means that half of the universe is going to be moving faster than the speed of light, and half moving slower. The half that's moving slower, he calls the material sector, and that's the half that we're familiar with. Coordinate space, 3 dimensions of space, and clock time, scalar motion in time. And this is the half of the universe that we're comfortable with and that we reside in. But in a different area of the universe, the relations would be interchange between space and time. And so in this faster than light area of the universe, which is a little bit of a misnomer, because the way that the the way that the system works is that the speed of light is 1, and on either side is 0. So over here is the material sector, where the speed is between 0 and 1. Over here is what Larson calls the cosmic sector, where the speed is beyond the speed of light. But once you get beyond the speed of light, it inverts. And so instead of saying that the speed is greater than the speed of light, you actually invert to what he would call inverse speed. So that the speed is, the inverse speed is less than 1. So once you cross that boundary, you don't keep track in units of speed, but you keep track in units of inverse speed, which is also known as energy, time over space, as opposed to space over time, which is speed. But that's semantical, but so beyond this speed of light, you have what's called the cosmic sector. And in the cosmic sector, you have relations that are based on coordinate time, 3 dimensions of time in a still frame, and clock space. And this is all blasphemy to the legacy scientists who say that the speed of light is the maximum speed of the universe. In a certain sense, just like I explained, it is, but they don't regard any of this cosmic sector stuff, even though the products of the cosmic sector, cosmic atoms and cosmic molecules, are what they would call antimatter or mesons. Okay, so you can again see the reciprocal relationship. In the material sector, you have 3 dimensions of space in a still frame and clock time. In the cosmic sector, you have 3 dimensions of time and clock space. Space is always getting farther and farther and farther apart. Now, to form an atom, you start with that initial progression. And then first you have to form a photon, which is done by some type of a reversal of that outward motion of the balloon, so to speak. And that results in a simple harmonic motion, a wave-like motion. And statistically, that motion is joined by another photon. So you have 2 photons oscillating around the same point. And then that motion has to be rotated in 3 different dimensions, again, because the universe is 3-dimensional. And then you have an atom. And so what you're doing is you're basically rolling back that outward progression and turning it into an inward gravitation. And that requires kind of all that formation of the photons, and then you eventually get what you call the rotational base. Then you get the subatomic particles. Subatomic particles are really only have 1 photon at the core, and the atoms have 2. I'm not quite clear on some of the details of that. But basically, when you do have matter or cosmic matter, then you also get relations that are based on the inside regions of both the material and cosmic sector. Because according to the discrete unit postulate, you need to have a full unit of space or time. And if you have atoms, then you have interactions of the atoms that occur in less than a unit of time. And if you don't have, or space, less than 1 unit of space in the material sector. And if you don't have a full unit of space, then you don't have space. And if you don't have space, then you have time only, because the universe is made out of space and time. And so Larson calls this the time region. And this is the region of atomic and molecular interaction in the material sector. And the rules reverse when you cross that boundary, that unit space boundary. And now the progression is moving inward and gravitation is moving outward. And that enables an interatomic equilibrium to be established at the point where the progression equals gravitation, knowing that the progression is constant and omnipresent, but gravitation is variable depending on the inverse square law. But every element and every molecule has a certain spot that they have that equilibrium. And so that equilibrium is then established in the solid state. And from there, that atom can be acted upon by things like heat. So that's where we're going to start off here with Larson's reading for today, having to do with the heat, or what he calls the thermal motion. When a molecule acquires a thermal motion, it immediately begins transferring this motion to its surroundings by means of one or more of several processes that will be considered in detail at appropriate points later in this and the subsequent volumes. Coincident with this outflow, there is an inflow of thermal motion from the environment, and in the absence of an externally maintained unbalance, an equilibrium is ultimately reached at a point where inflow and outflow are equal. Any two molecules or aggregates that have established such an equilibrium with each other are said to be at the same temperature. In the universe of motion defined by the postulates of the reciprocal system, speed and energy have equal standing from the viewpoint of the universe as a whole. But on the low speed side of the neutral axis, the material sector, where all material phenomena are located, energy is the quantity that exceeds unity. Equality of motion in the material sector is therefore synonymous with equal energy. Thus, a temperature equilibrium is a condition in which inflow and outflow of energy are equal, where the thermal energy of a molecule is fully effective in transfer on contact with other units of matter. Its temperature is directly proportional to its total thermal energy contents. Okay, well, I think I kind of got lost there pretty fast, but energy is inverse speed, and you can't use fractions in the reciprocal system, and so you end up using the inverse. So in the material sector, you cannot add units of speed directly. Instead, you modify that progression with units of energy. I don't believe I've stated that correctly. I'm going to have to figure out a way to say that a little bit better, but that's the general idea. You add units of energy in the material sector to obtain what is the equivalent of fractional units of speed. Okay, let's keep going. Under these conditions, energy equals kT. Where in natural units, okay, energy equals kT. In natural units, the numerical coefficient k is eliminated, and the equation becomes energy equals T, temperature. So energy equals temperature in natural units. Combining this equation with one of the equations from last chapter, we obtain the general gas equation, PV equals T, pressure times volume equals temperature, or in conventional units where R is the gas constant, PV equals RT. Okay, that's when you're going into MKS units. The gas constant is what's used to change from natural units to the MKS system. So I'm not sure why he put that in there even at all. It just seems to complicate the whole matter. Basically what we have is, I'm sure there's a reason and we'll figure it out, but it does seem to complicate the whole matter. I know that at least me, and I think a lot of you out there, are probably somewhat allergic to algebra, and just even these simple equations can be a little bit taxing, on my my liberal arts, brain here. So, but PV equals T, pressure times volume equals temperature. Okay, the last chapter was on compressibilities or pressure. So, you can do a check on that equation. Pressure is time over space to the fourth power. Volume is space to the third power. So you end up getting time over space is energy. I think I said earlier that that temperature was space over time, but here temperature is time over space. I said that temperature was space over time because I just remembered that Larson said that temperature is a speed, but apparently here it's an inverse speed. Temperature equals time over space. Okay, that doesn't seem to make sense to me either, but I'll have to think about it, because as the temperature goes up, I would think that the time would go down. Like the more temperature you have, the faster a reaction occurs. And so the time would seem to go down as the temperature goes up. So I'm more confused than you are probably, but let's just keep going on. Okay, these are the relations that prevail in the ideal gas state, which is a term of chemistry, I guess, that the ideal gas is gas that does not really, it's beyond far apart enough so that it's not really colliding with other gas molecules. Every one of these gas molecules is got a high rate of motion and they collide with each other, but in an ideal gas, I don't believe that's the case. So, but none, that kind of thing doesn't really exist. Okay, could be complicated even more, but let's just keep going. Elsewhere, the relation between temperature and energy depends on the characteristics of the transmission process. Radiation originates three-dimensionally in the time region and makes contact one-dimensionally in the outside region. It is thus four-dimensional, while temperature is only one-dimensional. That's got me lost too. We thus find that the energy of radiation is proportional to the fourth power of the temperature. So he's got energy of radiation equals K times T to the fourth power. So I'm guessing that would mean that the energy of radiation is time to the fourth power over space to the fourth power. This relation is confirmed observationally. The thermal motion originating inside unit distance is likewise four-dimensional in the energy transmission process. However, this motion is not transmitted directly into the outside region in the manner of radiation. So this is being the thermal motion. Not transmitted directly into the outside region in the matter of radiation. And again, the inside region is the time region. The outside region is what he calls the time-space region, or just the main region of the material sector. The thermal motion originating inside unit distance is likewise four-dimensional. Okay, so this thermal motion is four-dimensional in the energy transmission process, but is not directly transmitted into the outside region in the matter of radiation. The transmission process is a contact process and is subject to the general interregional relation previously explained. Okay, that's the interregional ratio. That's the amount that is lost in the translation when you are crossing boundaries and moving into other sectors or regions of the universe. And so when you cross from the time region into the outside region, you have to reduce by a certain fraction, depending on whether it's just radiation that you're talking about, or subatomic particles, or atoms. And let's see what he does here. Instead of E equals K times T to the fourth, as in radiation, the thermal motion is E squared equals K times T to the fourth. Because in the time region, you're dealing with what he calls equivalent space. And equivalent space is the spatial equivalent of time. Because in the time region, you do not have space, but we only see space because we are anchored to the material sector in the spatial reference system. And so we don't see space, or we don't see time, but these interactions are occurring in time. So the way that we see it is we see the inverse of what's going on in time, because space and time are reciprocals of one another, but we see it, everything that we see in equivalent space is a second power relation. Okay, we're going to stop right there, and hopefully he'll discuss this a little bit more as we move on, and hopefully we will get our bearings and figure out what's going on. Don't get discouraged. This is part of the territory. It's a detective work, so it'll be worth it. Thanks, and have a great